Hey everybody, this is going to be our video on chapter 3, which is in regards to what groups look like, where for us this is taking a very specific direction in looking at these objects called Cayley diagrams. Now, quite a few of these slides that I've used here are similar to what I had included in chapter 2, and that's mostly because I intended for these to be in chapter 3, but their inclusion in chapter 2 was to try and clarify a few issues we were having in understanding some basic concepts for groups. So the start of this and the start of our notes that have been posted has been this concept of constructing a roadmap for the Rubik's Cube. And the idea was pretty simple. While you were probably even in school yourself, because I had people demonstrate this to me when I was in middle school, is that there are many techniques that exist that allow for one to solve the Rubik's Cube without knowing anything about the Rubik's Cube. And what I mean is you can find online simply a set of rules that allow you to take any Rubik's Cube in any configuration and return it to the solved state by simply following the algorithm that they provide you. And these algorithms vary from very complex to very simple depending on how much effort or thinking you're willing to put into it to understand the algorithm. But roughly speaking, these algorithms are, one could think of as roadmaps. And so what I mean is they describe some kind of method that allows you to perform some sequence of moves relative to your starting point, and it gets you to the desired solved state. And this is what we really want to understand. We want to somehow say, okay, what if we could somehow understand every possible path to getting there? And you might say, well, why would you want to do that? Well, if we could think of a group as being the set of actions and all of the resulting compositions of these actions, then understanding this kind of roadmap would help us understand, let's say, structurally, what's going on inside this group. This roadmap would tell me what is the outcome of an application of any sequence of actions, and it would allow me to understand kind of whether certain actions have one type of behavior while other actions have a possibly different type. And a nice little tidbit is to know that it's actually been proven that every configuration of the Rubik's Cube is at most 20 moves away from the solved state. So even though we know that there's something like 4 times 10 to the 19th possible different moves that one can perform, no matter what configuration you have in your hand, you are at most, meaning less than or equal to, 20 moves away from the solved position. And so this tells us something kind of very intriguing about the group structure, which is even though that is vastly large, there is also a lot of interconnections that are happening here as well. And so what we're going to pretend, and this is called in the notes a thought experiment, we're going to pretend like we want to write a solutions manual for the Rubik's Cube. And so what do I mean by that? Well, a solution manual, let's say, could have lots of properties, but here are 3 that we could find relatively nice to hope for. Given any configuration of the cube, meaning you've handed it to your friend and they've scrambled it up, you now have that scrambled configuration. Let's say that we hope that there's a unique page in our solution manual corresponding to that configuration. Why would that be important? Well, we hope that there is a dedicated set of directions from your given scrambled state to all of the other possible paths that may lead us to the solution. So we want to have a very complete understanding of the cube's configurations. The other thing that we hope for is that there is some kind of method that allows us to find that configuration. So what do I mean? Well, when you open the Webster's dictionary, you don't have to play the lottery hoping you'll find your actual word. There is a method to the madness, and what is that method? Everything is sorted in alphabetical order. So what do I mean? We have all the A letters or words that start with A at the beginning, and then after that we sort based on the second letter in alphabetical order, and then the third letter, and so on and so forth. And so in the notes I propose, let's say, a particular way of sorting our configurations, but let's say it doesn't really matter how. Simply you should understand that there are a finite number of configurations. There are, let's say, 6 faces, each with 9 cubes on each face, and there are 6 colors, so clearly I could order things based on starting with a certain face and going through the different colors in each cube. And finally, we hope that with each configuration, meaning with each page, there is a list of available moves. And so what that means is it would tell you, okay, from this configuration, if you were to rotate this face in this direction, you get this outcome. And not only that, it would tell you whether that outcome was closer to the solved state or further from the solved state. Now, of course, we could squabble over what it means to be closer or further, but what we really are thinking is this. You are further away if it requires more moves to get to the starting, or let's say the solved state, than your original starting position prior to that move consisted of. So what do I mean? If I have the cube in my hand and I could solve it in 5 moves, but if a certain move results in needing to do 6 moves to solve it, that moves me further away. Whereas if a move moves me closer, it means that I now would only need to complete 4 moves. But once again, the details of this aren't terribly important because ultimately we're not going to write the book. And basically we're just going to call our solutions manual the big book because we're never going to publish this, so we don't need to worry about a catchy title. So as a sample page, let's say this is what we could do. And of course, we could all decide and agree that there are better ways to write and make this book look better, but since, once again, we're not publishing it, we won't worry. So the idea is, over here on the left, this is the particular configuration that I have in my hand, okay? And the idea is there is some kind of some kind of orientation to this, but loosely speaking, we can see all 6 faces by looking at the front and the back. Now the idea is I would be able to check that this is indeed my configuration, so I'm on the correct page. Now of course how I found this page could have been a cumbersome process, but we won't worry about that. So what we have here is we can do either a clockwise or a counterclockwise, meaning by 90 degrees, rotation of each face. And of course we could do a lot more moves, but let's keep it very simple. So what that means is each face, each of the 6 faces, has a particular move that can be performed, either counterclockwise or clockwise 90-degree rotations. And what we can see is, first of all, the book would tell me where the result is in the book, so I could find it very easily. And not only that, it would tell me whether or not I'm closer or further from the solution state. So what that tells me is, not only I know which ones are good, which would be the ones that are closer, but also I can very clearly see which moves are appropriate to perform in each of these cases. So, once again, this is a thought experiment, so this book or this page is completely made up. But this is just to let you know that this is what a solution manual should look like, in the sense of these are the features that it should have. Now, maybe you guys have seen these kind of books before. For instance, they used to exist. You can think of the big book as like a road map, and at each page it says if you are here, or it tells you that you are here, and then it says if you go in this particular direction you'll end up over there. And of course it also tells you whether over there is closer or further from your goal. And really this is somehow kind of like a choose your own adventure book, which maybe you remember. There are, I imagine you guys at least have heard of the concept of this. For instance, when I was younger, this was something that the R.L. Stine Goosebumps books had tried to consider at some point. But the idea is we have the ability to choose our own path, and of course we can choose to go the wrong way and eventually correct ourselves later. So, what are the pros of this big book? Well, we can solve any Rubik's Cube in any configuration. Given some configuration, every possible sequence of moves for this is in the book. And so, of course, these could be very long sequences where we took bad directions for a while and then corrected, or they could be very short sequences where we chose the correct turn every single time. And the big book contains the complete data on the moves or the actions that live in the Rubik's Cube universe, meaning all of the legal allowable actions. So in that sense, it really gives us a complete understanding of the group in the language that we had formulated in the previous chapter. Well, the cons are, of course, now the Rubik's Cube is no fun because we can solve it very trivially. If we had such a book, it would be very cumbersome in the sense that from our previous slide, we see that I would have to go to this enormously large numbered page before I even found what I was looking for. And of course, you could probably convince yourself that it would take you far too long to get here, that basically you would never use such a book. And finally, we can't actually make such a book. So what do I mean? Well, pretty much, if we were to make a book like this and let's say put one configuration, so one page, takes up 1 square inch on a page, a standard 8.5 by 11 page of printer paper, then all of that paper would actually cover the entire surface of the Earth many times over. Not only that, storing it inside of a computer is actually impossible. There is no computer in existence that I know of that could actually hold that much data. So not only would this be kind of an annoying thing to deal with, but we actually don't have the capabilities to deal with such a thing. So even though we can't handle this, let's say, so-called solutions manual, it doesn't mean it was a bad idea. It simply means that the group that we're considering is just very massive. So, but the big thing that we should take out of this is we simply constructed a way or described a way by which we could map a group. And so, of course, what I mean by a map can mean lots of things, but really the idea is we now have a road map that allows me to figure out how to get from point A to any point B inside of my group. So we're not going to just give up on this simply because our big book didn't work. We're simply going to consider a smaller group and hope that things work out better. So our simpler example is something that we introduced in the previous video, which is the rectangle puzzle group. And I'll go through things quickly again, but I want us to understand now that really what I want to do is completely map out this group. And so what I mean is I want to understand what performing each action will result in. So I don't want to just consider performing one action a couple times. I want to say, hey, give me all of the possible configurations. So if I want to perform one action 37 million times and then the other action in succession by 19 times, then I should be able to know exactly where I will end up. Now, by considering this puzzle group, it's actually the case that we saw in the previous chapter, the result's pretty small. So this is something very easy to envision. So our predefined list of actions, just as before, will be a horizontal flip and a vertical flip, and I'm color coding them to make it easier when we look at the picture. And of course, once again, this horizontal and vertical does not refer to any kind of axes of rotation, but the idea is a horizontal flip simply says put your right hand on the right edge of this paper and flip it over horizontally. All right. So of course we'll talk more about these things in chapter 4, but the reason that we have chosen horizontal and vertical flips really boil down to the idea that they preserve the orientation of the original rectangle. So what I mean is, for instance, one possibility would be a 90-degree rotation. And yes, it would still be a rectangle, but it would not be the same configuration of a rectangle. In much the same way that if I were to remove one face of the Rubik's Cube, flip it over so that I could see the inside and glue it back on, that would still be a cube. However, it would not respect the actual, let's say, physical structure of the cube, which is to have all of my colors on the outside. So in that same way, we're saying that we're preserving the fact that the top is longer and the sides are shorter. And anything that preserves that and also makes sure that it makes a 90-degree angle that's right here, or I mean that's a bad way to describe it, but basically saying that I need this edge to be parallel to the edge of my computer screen, then anything that preserves that is a valid and legal move. So, and of course we can ask ourselves if there are other moves, and the answer is yes. And in fact, if you've seen the previous video, you know that such moves exist, and we will explore them in a second. So, now of course this motivated in the previous chapter the question of whether this rectangle puzzle was a group, and the answer was yes. Now, why was it a group? Well, it was a group because it actually satisfied each of our 4 rules, which is there was a predefined list of actions, and that's usually trivially true. We have horizontal and vertical flips. Every action is reversible, and it's actually the case that each action reverses itself. Every action is deterministic because if I were to do a horizontal flip, there is no uncertainty about what the outcome will be. And any sequence of horizontal and vertical flips still result in a rectangle that is in the same configuration. So, now, the way that we kind of understood groups was through this picture right here. And this picture, I didn't go into details of why it was so important before, but is actually a thing that we hope to study here. Now, the idea of this picture is it is a roadmap of our group. So what do I mean? If we want to try and think of things in terms of the big book idea we had before, let's call the original solved state, let's say, for instance, page 1, even though this is where we're wanting to be. And if I'm on page 1, I ask myself, what are the possible things I can do? Well, I can perform a horizontal flip or a vertical flip, because those are my only 2 things that I really know how to do. And if I perform that, I'll either end up on page 2 or on page 3. Now from page 2 or page 3, I have the same set of actions that I can perform again. On page 2, I can either do another horizontal flip going back to page 1, or I can perform a vertical flip, which will take me now to page 4. Similarly, on page 3, I can perform a vertical flip to go back to page 1, or I can perform a horizontal flip to go to page 4. And from page 4, I see that anything I do will either send me back to page 2 or to page 3. So my solutions manual consists of exactly 4 pages, because I have exactly 4 configurations of my puzzle, and on each page there are exactly 2 paths that I can take from that page, meaning I can either go forward or backwards, loosely speaking. So this is our roadmap of our group. And in fact, there's nothing else that can come from this, because if I perform a bunch of horizontal flips, I simply go back and forth, back and forth, back and forth. Similarly, vertical flips, back and forth, back and forth, back and forth. And if I perform them in succession, I simply rotate through these 4 configurations. So this is my roadmap, and this is, I think, a really good way to actually understand groups is the roadmap that is generated from their actions. So, and what we talked about last time is, of course, since we're considering groups as actions, right? The idea is you are tempted to think of the group as the 4 configurations of the rectangle, but really we are thinking of groups as these actual actions, where we have the action of doing nothing, horizontal flips, vertical flips, and the composition of the 2, which is a rotation. So, our group consists of these 4 actions. However, if you prefer, you can think of our group as just simply these 4 configurations. As I said in Chapter 2, one can construct a bijective mapping, meaning a function that is basically a relabeling of my actions to the configurations. So this is a fancy mathematical way of saying what? It means that there's nothing lost in terms of information if you want to consider the configurations rather than the actions. All right? However, it does make working with our definitions a little bit harder at the moment, but for now, if it is, let's say, something that helps you understand your group better, there's nothing wrong with it. So, the idea is we need 2 actions to generate our group, and that all that requires is a horizontal flip and a vertical flip. Now, why is that? And this goes back to a question you guys had in Chapter 2. You might say to yourself, why do I need just horizontal and vertical flips? Well, once I know it's a group, then if we go back to the actual rules, Rule 2.8 says any sequence of consecutive actions is also an action. And on top of that, I know that every action is reversible, which means the reversal action is a valid action. And if that means if I have an action, I can reverse it for free. All right? So why do I mention that? Well, we might be tempted to say, I actually need all of these guys. But that's not true. If I have a horizontal flip, then for free, since I know it's a group, I can reverse the horizontal flip. And the composition of horizontal flip, meaning go this way, and reverse horizontal flip, which is go this way, the net result is nothing. Hence, I get this identity action simply by having this action and the ability to reverse something. However, I do need another action in order to get around the entire picture. So what I mean is if all I had were horizontal flips, then all I could do is go back and forth, back and forth, back and forth. So I do need the ability to go down in my picture. And so the idea is adding the vertical flip gives me that capability. And so then I can go from here to here, and I can go from here to here. Now, Rule 2.8, which says closure under compositions of actions, tells me that I can go vertical then horizontal, or horizontal and then vertical, which gives me a new action, which is equivalent to, let's say, a 180-degree rotation. So we have our set of actions, and not only that, we only need 2 of them to generate it, which is this guy and this guy. So this goes back to, for instance, the question regarding the integers. Many of you guys, and it's probably likely that I will give full credit for this, have submitted answers that said the generators for the set of integers is add 1 and add -1. And this is the right idea because you know that you can add 1 a bunch of times to get all the positive ones, and you can add -1 a bunch of times to get all the negative ones, and when you add 1 and -1 together, you get 0. So you can get the entire set. However, once I know it's a group, then I can take the action add 1, and knowing that its reversal is the action add -1, I actually only need the one single action, which is add 1, to generate the entire group, because I will reverse it to obtain all of the negative values. So it's not necessarily germane to the current chapter, but it's something I wanted to try and describe a little bit better through video. Now, so this is something that we've discussed before, so we'll kind of move on at this point. And some things to remind us is this group has a structure which is known as being abelian, which is the ability which means that reversing the order of my actions results in the same outcome. So some other actions that have a similar property would be, for instance, the addition and multiplication of integers and the addition of matrices. However, the multiplication of matrices is an action that does not have this property, right? We should know, basically from our previous from homework number 4, that when we multiply matrices in different orders, we're not guaranteed to get the same result. So, also in this group, we have a very strange feature, which is every action is its own inverse. And as I said before, most groups will not have this feature, but algebraically it's represented with the following expressions or relations. So, now what we want to talk about now is the fact that this group could be generated in a completely different way. And what is that way? We could generate the group by performing horizontal flips and 180-degree rotations. Now, the idea, though, is I still end up with the same exact 4 configurations of my puzzle. And I still have the same connections. Now, what do I mean? Let's go back and forth a little bit. So this blue line doesn't change anything. When I do a horizontal flip, I end up here. Now, when I perform a 180-degree rotation, I end up down here. And what you can see is, when I look at this page here, my horizontal or my 180-degree rotation corresponded to moving from here to here. But now I have this direct diagonal line. But if we look at the actual labeling, we can kind of see that everything still lines up. And in fact, everything is still connected. And so in that same way, I have the horizontal and the diagonal line. Now, we might start to ask ourselves, well, okay, I can't connect them in the same way. Well, that's true, right? There is a different path, loosely speaking, that we take. However, structurally, if I only consider the colors and I, let's say, erase all these numbers and all these labels, then what do I end up with? Well, I end up with something after I basically take this and unrotate it that looks exactly like this guy. And what do I mean? I have a white box, blue line, white box, red line, white box, blue line, white box, red line. So structurally, those are equivalent. And now, of course, this is where I start to lose people, because you say to yourselves, well, in mathematics, we learn that everything is very exact, very precise, and if we're not careful, then we are incorrect. And that is very true. But what we're doing here is not adding and subtracting numbers. We're not concerned with actual quantitative values. In algebra, we are concerned with qualitative features. And so what I'm saying is this object in some way similar to the previous object? And the answer is yes, it is. And of course, what this means is somehow these groups, even though they're generated by 2 different generators, are in fact equivalent. And this is going to be something that later on we'll call an isomorphism. And you might say, well, what does that really mean? It means that up to relabeling, this object and this object are structurally the same. And you might argue that labels are important. That's true. But what you could imagine is this is the description of our group in Spanish, let's say, and this is the description of our group in German. And as long as we adequately describe that group, then the language that we use is not terribly important, because the underlying structure is the same. And that's what we really have going here. And so I may have went too much in depth here, but I'm hoping to make this abundantly clear. Now, this diagram that we're considering is actually something very important and very special, and it's called a Cayley diagram. And the idea is, hopefully I've loosely convinced you that how you decided to connect everything was irrelevant. So what do I mean? Of course you have to connect them correctly, but what I mean is whether what you chose as your generators or which order you decided to lay out your white boxes in did not matter, because somehow these connections were preserved. I still ended up with a square that had colors, let's say the same color on the top and the bottom and the same color on the 2 sides. The fact that they were crisscrossed in the one simply corresponded to taking those 2 sides and rotating. All right. Now, the fact that I tell you that it's irrelevant in a way doesn't mean that you should just connect things in any way that you choose. We still hope to try and connect things in a way that are easy to read and still convey some level of symmetry. All right. Now, the official name of our road maps is actually something called a Cayley diagram, named after a mathematician, Arthur Cayley. And it's actually the case that Cayley was the first person to provide the modern definition of a group and many other important algebraic things. In particular, we wouldn't really be able to understand matrices without him. And the idea is, if you're curious, before Arthur Cayley, to everyone, groups were simply what we would call permutation groups. And what are permutation groups? It's simply saying if you have the numbers 1 through 5, how many different ways can you write the integers 1 through 5 while only writing them down once? So what I mean is kind of just shuffling them together, kind of like you do with a shell game. So before Arthur Cayley, there was no notion of anything else other than this shuffling idea. Now, so he provided this modern definition that, loosely speaking, is our current definition, which is the satisfaction of rules 2.5 through 2.8. So, and in general, a Cayley diagram is nothing other than a set of nodes that are connected by arrows. And typically these arrows are either colored or labeled so that we can distinguish the difference between them. And the idea is, for us in these pictures right now, an arrow of a particular color represents a specific generator, and the action of the group is represented by a unique node. So what do I mean? So if we go back, we can see that our group has 4 distinct actions: nothing, horizontal flip, vertical flip, and rotation. However, I can generate each of these 4 using only 2 colors, meaning only 2 generating actions. So that's what you should understand. These nodes represent particular actions, and the colored arrows represent the generators that we are using to generate the entire group. So, and the idea is each action, or let's say total action, is represented by a non-unique path starting from the solved state. So if we go back here, the action of rotation is represented by, well, in this case, a direct path. But then the action of a vertical flip is represented by a horizontal flip composed with a 180-degree rotation. So we have a non-unique path. What do I mean? This and this versus this and then this. So we have lots of moving pieces here, but here's the takeaway. In a Cayley diagram, every action needs a node. So in the Rubik's Cube, every node was a page in my book, but here for the rectangle, it's just simply 4 different rectangle configurations. Then we have that there are generators that move us in between these guys. So here, this is simply either a red or a blue line, but in the Rubik's Cube book, it was a description of, if you perform this rotation or this generating action, then you'll end up on this page. So we had a much more, let's say, verbal description of what was happening, but loosely speaking, it is analogous to this type of object. So the idea is these should be pretty clear from the rectangle group example, and since I've been going back and forth, I hope that it is clear. And let's actually understand better what these arrows are. So mathematically, the idea is pretty simple. Each of these nodes, X and Y, represent an action. Remember, the groups are the set of actions. All right? But if you want, as I said before, we can think of these as configurations in the group. So, but I'm going to continue thinking of them as actions. So I have an action X, and this is simply saying if I take my action X, and after performing the action X, perform the action G, then the result will be the action Y. So, in the language of our previous slides, I'm saying if I take the identity action and perform the H action, I will end up with the action Y. And you might say, well, that doesn't sound very descriptive because I'm saying that performing a horizontal flip is a horizontal flip. That's true. But then we can think of the following. If I take the horizontal flip and call that X, and perform the action of a 180-degree rotation, which corresponds to G on the slide that we were on, then the result is a vertical flip. So I have that G of, let's say, R of H is V. So I have a very different result. However, this is what these arrows represent. Now, if an action is its own inverse, which was exactly the case we had before, right? 2 horizontal flips result in nothing. Well, then the idea is if I apply H to A, I get B. And similarly, if I apply H to B, I get A. We use this double-sided arrow here. However, to avoid any kind of let's say overdrawing of features, we typically omit the arrows whenever we have a double arrow. So the idea is you cannot always omit the arrows. Arrows are only omitted whenever you have this kind of an action is its own inverse feature. Okay? Now, this is something I want to make clear, and this is a tough thing to talk about at times because so many of you guys, for instance, have maybe taken a discrete math course and you have some notion of what's called graph theory in your mind, and you start trying to impose your knowledge of graph theory on top of our Cayley diagrams. And let's say in some sense that's not a bad idea. One could study Cayley diagrams for their graph theoretical properties. However, at the moment, I do not want us to try and do that because I think it's just going to introduce more problems than we really care to consider. And what do I mean? It's going to be very likely that you'll think of a graph theory concept and you'll try and apply it and it'll work, and there'll be this kind of correspondence, and you'll say, oh, my graph theory idea is the same as this group theory idea. And sometimes that's true, although sometimes you just got lucky. So I'm trying to avoid the situation where we have the added confusion, which is really a result of pure luck, right? So let's say if you don't know what graph theory is, obviously ignore the last 3 minutes of me talking, but I want to make sure we understand the concept of arrows, which is saying that if I perform the action G on my previous action X, I get the resulting action Y. And that, I hope, makes sense based on our previous pictures. And we'll see some more pictures later. So once again, this is what I was saying. This picture here, this very uninteresting picture, is exactly all that matters in the previous rectangle puzzle group. So what do I mean? No matter what the situation was, I had some 4 white nodes that were connected by colored arrows in this particular sequence. Now remember what we had before is if I basically rotate, taking this node, picking it up, and moving it over here, these red lines would crisscross, and that would look like my previous structure. But if we assume that our Cayley diagrams are basically infinitely flexible, then there's no difference here, right? Somehow this simple picture encodes all of the information about the rectangle puzzle group. Now, why is this important? Let's consider another group, which is the 2 light switch group. Now in the notes, I obviously have a far better picture of this, but for the sake of, let's say, space, I'm trying to consider something a little simpler. So remember, the 2 light switch group is pretty simple. You walk into a room, there are 2 light switches on the wall, dictated by this, and being good people, they were both in the off position because no one was in the room. Now, we ask ourselves, what is the structure of the group, if it is a group, if we only have 2 actions, which makes sense? Turn on the left light switch or turn on the right light switch. Well, let's see what happens. Of course, there was the identity action, which was doing nothing. I can flip up the left light switch. I can flip up the right light switch. And if I do left then right or right then left, in both cases I end up with both light switches flipped up. Now, there are no other possible configurations of these light switches, and that should be pretty clear because we're excluding the option to, for instance, balance it exactly in the middle where the light kind of flickers on and off until it figures out which direction it's going, right? The action is very clear. It has to flip it completely. So with this and with these colors, I think what you should start to say to yourself is this picture looks an awful lot like this picture, where this picture represented my rectangle puzzle, but somehow here I'm talking about light switches. Now, this is a very good observation if you've made it. If you didn't make it, you can pretend like you made it and nod along and say, yes, that's a very astute observation. But that is really what lies at the guts of abstract algebra. I would like to study an object and then understand what other objects look like this object I've just studied. So what I'm really getting at is, look, I have the light switch problem and I have the rectangle puzzle problem. Algebraically, in terms of these Cayley diagrams, they look pretty much the same. And what we hope then is by looking the same, they have similar algebra properties, and by studying one, I know something about the other for free. And this is truly what lies at the heart of abstract algebra. Basically, they say in math there's no such thing as a free lunch, meaning that you can't gain something without a little bit of work. But in algebra, there is somehow the sense of, well, there's no such thing as a free lunch, but if I buy supper and have leftovers, I can eat them the next day. And that's exactly what we have going on here. Here I'm going to study this problem and I'm going to really try and understand it, meaning buy supper. But then, the next morning I'm going to wake up and say, oh look, Look at this guy. Well, basically, this is my notion of leftovers. I've already done all this work at supper. I paid my bill. But now I understand what this looks like because I've already spent the time, and that's what we gain from algebra. And of course, this is a very simple problem that we could have probably understood in other ways, but then you could see how as I make these more complex, this becomes a desirable feature. So the idea then, once again, is that the rectangle puzzle and the two light switch group have the same structure given here. And it's actually called the Klein 4 group. And so the idea is, to me, from an algebraic viewpoint, I see no difference between the rectangle puzzle and the two light switch group because they are both examples of the Klein 4 group. And later we're going to learn they're equivalent through something called an isomorphism, or a relabeling of the particular scenario. So the idea is, even though the way we understand them, they're fundamentally different objects in the sense of physically how they're realized, the way that their actions result, right? So kind of, let's say the way the actions work together and create results is exactly the same in structure, right? Now we denote the Klein 4 group by V4, and the idea is this is, of course, from a German thing called a Vierergruppe, which, of course, my German is bad, but the idea is this is just German for 4 group, and it's named after the mathematician Felix Klein, whom you can feel free to look up. And so the idea, another idea is the following. We got to make sure we avoid the confusion where we say, hey, look, this is a square and this is a square. But these are not the same squares. They're fundamentally different. Why? Well, even though I have 4 nodes and I have a square shape, here, the fact that there are no arrows imply that I can go from here, let's say from left to right and then right to left for free. But this implies that I can go left to right, but I can't go back. I have to go down and then over and then up to get back there. So structurally, this is very different. It actually has a very qualitatively different feel. So this is not another example of the Klein 4 group. It is just another group that happens to have 4 distinct configurations. All right? And of course, we could ask ourselves, what would be such a group? And maybe you should think about it. And the idea is, of course, you could pause it right now and try and write down what such a group would be. But actually, this is a pretty simple group. Let me label this 0. Let me label this 1. Let me label this 2. And let me label this 3. And then let me let this blue arrow pointing in one direction be the action add 1. So if I'm at 0 and I add 1, I'm at the number 1. And then if I'm at 1 and I add 1, I'm at the number 2. And then if I'm at 2 and I add 1, I get to the number 3. And then this is implying that when I'm at 3 and I add 1, I should get 0. And you might say that sounds strange, but this is exactly the group of integers modulo 4. So we have seen this group, and in fact this is a different group because it can be generated with one action and in fact has a very different looking structure. So it has this kind of repetition that has a certain length to it that I can't really alter without adding something, or let's say considering the action of adding 2 and then adding 2. All right. So this is something you'll consider in the homework, but this is just to clarify what group this does represent. So this, of course, motivates things that I consider to be natural questions, which are the following. What group has a Cayley graph like the diagram on the right? Well, we just said it was the integers modulo 4, where the action is addition modulo 4. How would you give a proof or a convincing argument that these two groups have truly different structures? Well, here's something pretty simple. For these things to be equivalent, they have to basically have the same structure. So what do I mean? If somehow I'm claiming that groups are equivalent when they're basically just relabelings, this is saying that there should be an action that when I apply it, I go somewhere, and then when I apply it again, I go back to my original starting point. However, what I see here is there is no action for which that is the case, right? Now, of course, we could start to say, well, look, there's the action of adding 4. Well, that is true, but the idea of adding 4 doesn't take me to a completely different place, whereas the horizontal flip action took me to a completely new place. So structurally, qualitatively, we have something very different here, and that would be a convincing, let's say, pseudo-proof, where I've shown you that this thing has a feature that this one does not, and vice versa. So they're not the same groups. And finally, you should ask yourself, okay, I now have two groups that each have size 4, meaning 4 distinct nodes. Are there any others? All right? And you might say, okay, I can come up with some, but then you have to convince yourself that group that you just came up with, does its Cayley diagram still look like one of these two? right? Because I know immediately what I could say is, for instance, consider the integers modulo 8, where my action is adding adding multiples of 2, for instance. Well, then I would go 0, 2, 4, 6, 8, which 8 is again 0. So structurally, that's still the same object. So you have to be very careful to convince yourself that if you come up with something new, it is indeed different. All right? So, to provide a little more clarification, let's play another puzzle. So, and this, of course, is related to one of your homework problems, but that's fine. So instead of the rectangle puzzle, let's play the equilateral triangle puzzle. So we label the nodes arbitrarily, and the idea is any allowable action is an action that when I perform it, I have a triangle whose base is down at the bottom and it points directly up. So what would be such an action? Well, doing nothing, for instance, or performing a 120-degree rotation, or performing two 120-degree rotations. The idea is you can draw this on a piece of paper and perform these rotations to convince yourself of the truthfulness of this. However, this should make sense. Why? Loosely speaking, you can think of inscribing this inside of a circle and doing circular rotations and seeing that it would preserve this orientation. You could also flip it horizontally. Now, what do I mean? By horizontal flip, I mean draw a vertical line through the top and take this point or this corner and move it over here, which would force this corner to move over here. So this preserves the triangular structure of it. Also, you might say, well, I could rotate across this axis. That's true, but it's actually going to be equivalent to either doing a single rotation and then a flip, or two rotations and a flip. So this triangle puzzle group is typically denoted D sub 3, and it has 6 distinct actions. And I'm telling you these are your actions, and for now you should believe me. But here's what you should do. You should pause the video at this moment, and you should write down all the possible ways that I can order these 3 numbers inside of the triangle. All right? And what you should get is, there is, of course, 1, 2, 3, then there would be 2, 3, 1, and then 3, 2, 1, and then there's, of course, 1, 3, 2, and, you get the idea, but you should come up with 6 different orderings. All right? And these should correspond to these 6 actions, but we have to convince ourselves of the truthfulness of this, because I could have written down some orders that maybe just don't make sense or aren't illegal, or they are illegal. So, if you were to write down your 6 configurations in their own individual triangles, then here's what you can see. Now, this Cayley diagram is a little more complicated, but here's the loose idea. The identity action is simply taking this guy and doing nothing. Now, let's go back and see that I denoted a horizontal flip by the blue. So, moving from here to here via blue is performing a horizontal flip. What is it doing? It's switching the order of 2 and 3. That is a horizontal flip. Now, similarly, if I'm in this configuration, performing a horizontal flip along this blue line goes here. Now, why are there no arrows on the blue line? Because if I perform the horizontal flip again, I end back up in the original spot. Similarly, the horizontal flip of this guy moves me here. Okay, so I now have obtained, let's say, 3 different configurations from this one action. However, they were being applied in multiple ways. So what do I mean? If I start with this configuration and I perform a rotation, then what am I doing? Remember, a rotation is defined as 120 degrees of a rotation. All right, and the idea is, let's say, maybe I wasn't very clear about the directionality to it, but let's say, based on the way I've written this, that it's a clockwise rotation. So what happens? A 120 degree rotation will move 1 to 2, 2 to 3, and 3 to 1, which is what I have here. Performing an additional 120 degree rotation doesn't send me back to the original. Hence, there is the one-sided arrow here. It sends me over to r squared, which was an additional rotation. All right, it's a distinct action, right? So the idea is I have, let's say, the horizontal flip, and then I have a rotation and a rotation squared, and I have the identity action. So now we have 4 actions. What happens if I perform an additional rotation? I go back to the original spot. So performing 3 rotations is the same as doing nothing. Well, why is that? 120 plus 120 plus 120 is 360. And a 360 degree rotation is the same as doing no rotations. All right? But then we have the other kind of compositions, and what are they? We have the notion of doing a flip and then a rotation, or we have the notation of doing or the idea of doing 2 rotations and then a flip and so on and so forth. And the idea is you can convince yourself that no matter what else I do, those are the only 6 distinct actions that I have, right? So the idea is we have here, from here, flip and then a rotation squared. If I perform an additional rotation, it's equivalent to just doing a, let's say, 1 single rotation and then a flip, all right? So, of course, you should take the time to really dissect this diagram, but what are you gaining from this? Now we've seen a different type of group with a different number of elements, and we see that there can be complications here in terms of how we have to draw them, but loosely speaking, we just need to lay out all of our possible configurations or actions and then connect them appropriately, all right? And how would I do that? Well, basically, I could start at this guy and say, well, what happens if I perform the identity? Nothing, all right? Then what happens if I perform a flip? I go here. What happens if I perform a rotation? I go here. So I have nothing, flip, rotation. And then what do? Okay, move to this guy. What happens if I do nothing? Well, of course, I stay here. What happens if I do a flip? I go back. What happens if I do a rotation? I get a new answer. Similarly, when I was right here, this was the other one I generated from the identity. If I perform a rotation, I end up here. And if I perform a flip, I end up here. So when I'm right here, flip sends me here. Rotation sends me here. And if I'm here, flip sends me somewhere I've already been. Rotation sends me somewhere I've already been. Here, flip, rotation. So we see that we start to get repeats. And if I continue applying my actions, I can convince myself I will gain nothing new. All right, sorry for spending so long on this, but I wanted to make sure it was clear. So D3 has 1 set of generators, which is just rotations and flips. The idea is anything else that you try and use as a generator would not be sufficient. For instance, trying to use r squared, I would still need r, and you should try and convince yourself of that fact. Also, we have relations, and what are relations? They're basically algebraic equations, which is what? 3 rotations is the same as doing nothing, which is what we convinced ourselves of. Similarly, 2 rotations is the same as undoing a rotation. A flip undoes a flip. Rotating and then flipping is the same thing as flipping and then rotating twice, which of course means what? This is not an abelian group because I can't reverse for free. Similarly, rotating twice and then flipping is the same thing as flipping and then rotating. So we have some very interesting relations. But these are things that tell us, and later we'll talk about this more, but for now these are just interesting observations. These tell us important features of our group. So we've had this triangle puzzle, and hopefully this is starting to make sense. We have the Rubik's Cube, we have the light switches, we have the rectangle puzzle, and now we have the triangle puzzle, and we're trying to build up just some examples in our minds. Now, what are some other observations we can make here? What you should observe is, for each action, meaning each triangle, then there is exactly 1 line of each color leaving this configuration. So what do I mean? Even though this is an arrow that looks funny, one of the arrows is leaving and one of the arrows is coming back. So I have exactly 1 blue arrow leaving and 1 red arrow leaving. All right. Now, what does that really mean? Well, each arrow is somehow a concept of, let's say, an action. What would it mean if I had a red arrow that goes out to here and a red arrow that goes out to here? Well, that means if I'm sitting right here on this triangle, I can simultaneously go here and here by performing 1 single action. All right? Now, what would that mean? Well, somehow this is violating the notion of deterministic. Why? Well, if this was a quarter, well, then what we can think is if I flip it, I either get heads or I get tails. And so the idea is both of these are equally probable, so there is no deterministic feature to it if I have multiple things emanating out from here. Now, that doesn't mean I cannot have multiple things coming in necessarily. We haven't convinced ourselves that that can't be the case. But the idea is for each color, it can only leave an action in 1 direction. All right? So we have this notion of deterministic is kind of represented here. We have the notion of reversibility. Now, it's not the so down here, reversibility means if I perform the action again, I get back. But here, reversibility is actually a little bit different. It means that if I go here, as long as I do R, meaning rotate 2 more times, I go back, or I can do what? Rotate, horizontal flip, rotate, horizontal flip. That is also a reversal. All right, and the idea is, let's say there's nothing that said that our reversals have to be unique. Now, of course, they're not a distinct act action because somehow they've resulted in the same configuration. But what we see is there can be multiple paths that represent a reversal, but if I'm in any configuration and I move to another, I have some path that exists that takes me back to where I started. Rule 2.5 is represented in terms of the fact that I have generators, which are the blue lines and the red lines. Those are my predefined list of actions. And finally, the fact that I don't somehow break the problem by performing these actions represents Rule 2.8. So we can see exactly how each of these rules start to play in to the structure of this Cayley diagram. All right? And of course, I've asked you some questions about that in your homework that I'm hoping this helps nudge you in the direction of correct thinking. So, what are some properties of these Cayley graphs? And really, this is just going to be something pretty simple. And this is also a question that I've asked. So observe at each node, there's exactly one outgoing edge of each color, which is something that I have already pointed out. So the natural question is, can an edge in a Cayley graph ever connect a node to itself? Basically, can I take this action and it just loop onto itself? Now, this should seem like something that makes sense. Why? If I were to give the identity action a color, then this would be exactly what it represents, right? The identity action would simply take whatever I apply it to back to itself. Now, why are we not considering the identity action in any of these things? Why does the identity action not get its own color? Well, it cannot generate the group. Basically, it gives me no extra information. So I could add it, right? I could add a color green, and basically what it would do is everywhere it would go loop, 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 loop. By adding this identity action as a color, I would get 6 green loops that tell me nothing about the group. So basically, let's say, of course, an edge can connect a node to itself, but then that would mean somehow that it was the identity action, and then the question becomes, should I have ever included it? Because I'm somehow saying that we should only use generators inside of our Cayley diagram. And before we go into question 2, why are we only including the generators? Because otherwise things get very complicated, right? You can think, if I'm back here, there's nothing lost by adding my green loop for the identity action, but there's also nothing gained other than the fact I have cluttered my picture up even more. So we would like to somehow reduce the clutter by only considering generators. That's the bigger idea. There's nothing wrong with using extra features, but the idea is we will have lots of repetition and a very messy looking diagram. So, question 1 by itself, it does seem possible that I could do this. Question 2 though, could I have an edge that basically does the following? Let this node be X, G applied to X sends it back to X. But if I apply G to Y, it will send me to a different node Z. All right, so what do I mean? Can there be an action that is an identity action in one place, but not an identity action in another place? This is a very good question, and if you think about it, you should probably come to the conclusion that based on the rules, there's nothing that forces this to not be an option, right? What you should say to yourself is, this feels funny. I don't like it, and I hope that this is not the case. But at the moment, there are no rules that force this to be necessarily true. So we're asking ourselves, can this simultaneously happen? And fortunately, the answer is no. So, we will now prove our first algebraic theorem, let's say, which is the following. Suppose an action G has the following property, which is that G of X equals X. So what is that saying? If I apply G to X, I get back X. And this is true for some action X. So I'm saying this is not G applied to itself. Why am I excluding that? So remember, if I let G be a horizontal flip and I apply it to a horizontal flip in the rectangle group, then the idea is we can end up with an identity or something like that. And that doesn't necessarily preclude us from this situation. But there are very strange situations where maybe somehow an action applied to itself could end up giving you the same action again. And let's say, what could those things be? Let's not worry about it. But the idea is I'm trying to say, let's assume that this X is different. All right? But there's nothing lost by considering the case when maybe it is. Then the result is, if this is true, G applied to some other action gives me the same X, then G has to be the identity action, meaning what? That if I apply it to anything, it leaves it unchanged for every single element. So think about what this means. If we have this scenario, at some node it maps itself to itself. Then it's saying this second scenario is utterly impossible. Right? And I know that sometimes it's difficult to dissect theorems, and I'm hoping that we understand the theorem prompt. I'm saying if you have this somewhere, then G has to be the identity, meaning it cannot do this, it does this everywhere. So you can't have this sometimes, you get either all or nothing. All right, how do you prove that? Well, by definition, it's actually the case that every action is reversible. So, for instance, H inverse doesn't necessarily mean perform horizontal flip twice. Okay, so let's be very clear what this notation means. This means that if I perform an action, this is the undoing of it. For a rotation, if H was the rotation, H inverse is 2 rotations. However, the idea is notationally, I'm saying if I have an action, I can reverse it, and that reversal is the ultimate outcome of doing nothing. All right. Now, assume that there's some action G that is not the identity, such that G of X equals X. All right. Well, what can I do? X has a reversal action. So let's apply the reversal action to the sequence G then X, and then let's apply the reversal to X. So what we're saying here is the following. I did G then X, now do reverse X. And then on this side I did X, now do reverse X. Well, what happens? X and X reverse will cancel themselves, and X and X reverse will cancel themselves. And what do I get? I get that G is equal to the identity, which is a contradiction. And what was my contradictive assumption that I've introduced? I assumed that G was not the identity, and this statement was true. So, since this is a false statement, what does it mean? Well, it means basically that if this is true, then G must be the identity, which completes our proof. All right, and actually this is a very simple proof, and it's one I want to make sure you understand, so you should spend some time looking at it. But another thing that you should take from this is you should ask yourself the following, that you could prove to yourself using something simple like this. You should start to ask yourself, okay, if it is the identity, am I guaranteed that the identity is unique? And these are questions that you should be asking yourselves as an algebraist. We're doing these algebraic studies, and then we have to start asking ourselves, are things unique? Are there other options? And so, is the identity action unique? Now, what do I mean? I don't mean in the sense that in the integers modulo 4, adding 0 and adding 4 result in an identity. But remember, in Z4, 0 is an equivalence class that actually already contains the number 4. So in that sense, that identity was already the same. So we start asking ourselves, are there identities that are in fact different, meaning not in the same equivalence class? And that's a very fundamental question. And the answer to that question is no. The identity is unique, but we have to actually prove that to ourselves. So that is something that, for instance, on scratch paper or as an aside, you can try and convince yourself of, and maybe we'll discuss it more later. So I hope this video was helpful. Of course, just as before, if you find typos, feel free to pass them on to me. I'm almost certain that I will make them, in the sense that I try and proofread everything, but it has just been the case that people tend to find little typos that, of course, your mind, as you read things, it starts to tell yourself that what you've written is correct after a certain number of read-throughs. So if you find typos, let me know. Also, if you have questions, let me know. Remember that we are now taking 2 weeks to do the homework assignments, so make sure that you keep that in mind. So even though this next assignment looks a little bit longer, make sure you remember that you have 2 full weeks to complete it, but also don't let that kind of lull you into a false sense of security, and don't put it off until 2 weeks from now. Actually take the time to start it. All right. So I hope this was helpful, and of course, like I said before, if you have any questions, feel free to let me know. Thank you, guys.